Okay, so next here, I think this one you can just take your tuition note and just go through it. Question number 4. This is textbook question 1 on page 34, okay, of your textbook. You can see later in this is the question on the textbook. In a reaction, 5.3 gram of sodium carbonate reacted with 6 gram of ethanoic acid. The products formed were 2.2 gram of carbon dioxide. So these are the products. 0.9 gram of water and 8.2 gram of sodium ethanoate. So 3 products were formed when 2 reactants reacted. Show that these observations are in agreement with the law of conservation of mass. Now, what does the law of conservation of mass says? It says that mass cannot be created nor destroyed. In other words, the mass, total mass of the reactants on the left side should be equal to exactly total mass of the products on the right side. If we can prove that, then we can see that this reaction is in agreement with law of conservation of mass, right? So here sum of mass of the reactants means on the left side, reactant 5.3, so here 5.3 gram, 6 gram of ethanoic acid. They reacted means that those are the reactants, sum of these two added 5.3 plus 6, you add 6.0, then you will get here 3.5 plus 6, 11, so 11.3 grams. Then this is the rough, okay, sum of mass of products. The products here, the products 2.2 grams, so here 2.2 gram, 0.9 gram of water, so here plus 8.2 grams, so the 3 products 8.2 gram of sodium ethanol. So when you add this 2.2 added to 0.9 added to 8.2, we have to make sure decimal is on the same line, right? 9, 10, 11, 12, 13, so 3, 1 in hand, 8 plus 1 in hand, 9, 10, 11, so 11.3 gram. So sum of the reactants is 11.3 gram, sum of the products also 11.3. So no mass was created, new mass added, or no mass was destroyed, no mass was lost. It did not become lesser than 11.3, same. So the law is proved. All right, so this is the law is proved. I hope that makes it clear to you. Okay, now go to the next question. So question number 5, textbook question 2, page 35, you'll find this. Hydrogen and oxygen combine in the ratio 1 hydrogen to 8 oxygen by mass to form required to form water. We know this. We did that right in the video 1 and 2. What mass of oxygen gas would be required to react completely with 3 gram of hydrogen? So here we know, given here, see 1 gram of hydrogen. See hydrogen first, so 1, oxygen second, so 8. 1 gram of hydrogen completely react with 8 gram of oxygen according to the information from here to here, right? Then 1 gram hydrogen react with 8 gram oxygen. So the question is asking 3 gram of hydrogen will react with how much oxygen? So if 1 gram react with 8 gram of oxygen, then 3 gram of hydrogen will react completely with 8 into 3, because it's just like 1 mango rupees 10. So how much will 2 mango be? Common sense. Yes, you're right, rupees 20. How did you get that? When you multiply this 10 to 2, 10 to 1 mango price 2, number of mango 2, then you get 20. Similarly, 1 mango 1 gram equal to 8. So 3 gram will be equal to 8 into 3, just like you did 10 into 2. So 24 gram of oxygen is the answer. I hope that's clear. Okay. Number 6. Which postulate means point of Dalton's atomic theory is the result of law of conservation of mass? That means which point in Dalton's atomic theory help us to discover the law of conservation of mass? The postulate of Dalton's atomic theory, which is the result of the law of conservation of mass, is this one: atoms are indivisible. That's why, because they cannot be divided, the mass was conserved. No mass was lost or created. Indivisible particles which cannot be created nor destroyed in a chemical reaction. Because Dalton proved this one to us, we were able to derive the law of conservation of mass, which says mass can neither be created nor destroyed. This you'll find in question 5.2 that we'll study just now. This point, see, question 5.2 help us to get the law of conservation of energy. Atoms are indivisible particles because they cannot be created. They are indivisible, they cannot be created and destroyed, therefore. So this has helped us to derive the law of conservation of energy, and we know today that's true because of Dalton, right? Now, which question number 7, textbook question 4, okay? Which postulate of page 35 textbook? Dalton's atomic theory can explain the law of definite proportion. So the postulate of Dalton's atomic theory, okay, the postulate of Dalton's atomic theory, which can explain the law of definite proportion, is this one. The relative number and kinds of atoms are constant in a given chemical reaction. Dalton said that in water, the relative number and kinds of atoms, like the relative number of atoms is in water H2O, 2 hydrogen always combined to 1 oxygen atom, and kinds of atom also always same in water, H and O, only no other atoms like nitrogen will not appear in water. That was given by Dalton's theory, which says the relative number of atoms and kinds of atoms are constant in a given chemical substance, and this is found in question 5, point number 6. Question 5, point number 6. So you see here, question 5, point number 6. The relative number and kinds of atoms are constant in a given substance. Well, I hope these are things you can read yourself without explaining, and I think you can get, because we took time to explain the Dalton's atomic theory detail, right? Now, next question. What is an atom? Okay, just know it like this for now. As you go on, you'll easily pick up. Atom is the smallest particle of an element that can take part in a chemical reaction. Just keep that in your mind, okay? Then, next one. How big or small are atoms? We cannot see atoms because they're so small. So we want to know how small and how big. If it's so small, how small? Okay. So you take more than millions of atoms and stack them up like you stack peppers, okay? Like this pepper, you stack up millions of pepper and stack up, then you'll get 2-3 story building now. So thin pepper, also million pepper means would be so huge, but atoms are so small that if you stack up peppers, atoms like this, one atom, two atom like this, one over another like this, like stacking up pepper, then if you stack up 1 million atom, okay, that 1 million atom will be just as thick as this one sheet of paper. 1 million atom put one over another will be so thin. That means it's so small. That's why we cannot see with our naked eye. So let's just read before we go to next. More than millions of atoms stacked would make a layer. So only one layer stacked to make a layer, sorry, will be barely as thick as this sheet of paper that you're holding, this one, single sheet. That is how big or small atoms are. Imagine that. Number 10. Dalton was the first scientist to use symbols for elements. Yes. Before Dalton, elements were known by their full name. Okay. Sodium element we always write like this. Sodium element means we write like this. Scientists were writing sodium element, carbon element. So it took long time and it was long process. But Dalton was the one who to use symbol. Symbol means short form. He was the first scientist to give it. Because of him, today we are able to write elements in symbolic form, which is simpler. Okay. Now, in Dalton's symbol for elements, the symbol also meant definite quantity. So when Dalton gave the symbol for element, it does not mean only the name of the element to identify the element, but it also meant how many atoms were there. Okay, that element, that is one atom of that element. So each of his symbols represented only one atom of that element. It also not told you what element it is. The symbol of the element given by Dalton also told you there was only one atom. It specified the quantity also. For example, his symbol for hydrogen, can you see here? So Dalton's symbol for hydrogen given was question number 10. Hydrogen, today we use the symbol for hydrogen, very simple, H, but Dalton was using this. Today we no longer use this. Okay, so this symbol also meant, this symbol here also meant hydrogen, one atom of hydrogen. Yes, we no longer use this today. Okay, number 12. The scientists who suggested that symbols of elements should be made from one or two letters of the name. Okay, element is given by the scientist called Berzelius, the one who, yes, suggested that elements should be represented by one letter or two letter, at least one or not more than two letters, is Berzelius. Okay, no element has three letters. For example, today we have the symbol for element as sodium as Na, carbon as C, okay, chlorine as Cl, and then potassium as K. So these all elements have one letter or two letters, not more than two letters. That was suggested by Berzelius. Okay, now very important question, simple, but just go through this. Briefly explain how IUPAC. For IUPAC means question number 13. Okay, question number 13. IUPAC means, you can write it down, International Union, on your copy. Question number 13. For pure and applied chemistry. Applied, APPLIED, applied chemistry. This is a union, just like Naga Students Union or Naga Students Federation. Okay, or Lotha Hoho, like that, no? So International Union for Pure and Applied Chemistry. So this union is responsible for giving us symbols, names of naming of chemical compounds in chemistry. Okay, now let us read through this. Question number 13. Briefly explain how IUPAC gives us symbols for elements. And all over the world we follow IUPAC symbol for elements. No, IUPAC approves names and symbols of elements. Many of the IUPAC name symbols of elements are the first one or two letters of the elements name in English. Most of the elements are derived from English name. The first letter of the symbol in an element is called uppercase. Okay, which means, okay, we'll explain that later on. It's always capital letter. And the second letter, lower, is called lowercase. If there is two letters, then the second letter is called lowercase of a symbol and should always be small letter. That's the rule from IUPAC. Some symbols are the first and the third letter also. Most of the elements are first two letters, but some are first and the third letter of the name of the element. Okay, and some symbols are from Latin names also. Not only English, most are from English, but some elements derive their name symbols from Latin names, not English. And the third letter, Latin names. For example, symbols of sodium is not derived from English sodium, but derived from the Latin name natrium, first two letters, sodium. Gold, AU, first two letters of the Latin name. This also, gold is English. AU is not derived from English name gold, but from Latin name aurum. Aurum is gold in Latin. Potassium is not derived from English potassium name, but Latin name kalium, the first letter K. Carbon is not derived from, calcium is not derived from English name calcium, but from the English name, sorry, first two letters. Carbon is derived from the English name C, first letter. Chlorine derived from the English name first and third letter. You may be getting a little bit, but to get it very clearly, let us go into booster one. Now this one you will find on your this one, okay, on your note, the tuition note that you got when you took admission. So go to page J in the beginning, okay, in the beginning part, this booster one, and let us do this together. And after you do this, you will clearly understand that question 13 yourself without explaining also. So next video will be on this, okay.